Okay, so that's that on checking to see if correlation is significant or not. Then we'll talk about linear regression. Okay, so yeah, correlation gives us an idea of whether or not a linear relationship exists, and then once once we've established that a linear relationship exists, we can do the application, which is linear regression. And again, linear regression is the most basic form of regression, which is, but it's incredibly useful, okay? So, I mean, don't let me knock it, okay? It's incredibly useful. It's just the most basic form of regression. And if you take another statistics class, you can take one on regression and you'll learn all sorts of exciting things, okay? But we're just going to cover the basic form. All right, and the idea behind linear regression is, as I think what you're accustomed to, or what you expect, and that is, so we have some data points. We've got data points, and we want to fit a straight line to summarize or best describe these points. Okay, so we want to fit a line that best summarizes the relationship. And so the question is, well, how do we choose which line is the best? Okay? Well, which line? Alright, so let's, if you don't mind just redrawing this somewhere in your notes, because this is what I'm going to use as our example here. Just this example with the data points 1, 2, 2, 6, 3, 4, and 4, 8. Okay? So let's just use this data set as our best. Our example here, and we're going to try to see how do we decide what line is best. Okay? So, so one candidate for a line would be something like that. Okay? Alright, and what would the equation of this line be? So this line is y equals 2x. So this is one candidate. And another one. Just this here. Maybe looks like that. Okay. So that's another candidate. Let me say this one is equal to y equals 1 plus 1.6x. So I know you guys are probably used to the form y equals mx plus b, but I write them I put the intercept first and then the mx part afterwards, and we'll get into that in a moment. So this is another candidate, okay? That one seems also reasonable. And let's just throw in a terrible line just for fun. Okay. And we'll say this one is y equals 6. Alright, so I think we can pretty much say this line is not going to be a good fit. Okay? But which one's better, this one or this one? Okay? Well, the way we decide Alright, is it okay that all of these lines here? Alright, so this is how we're going to decide which line is the best fit, okay? So I have to introduce the concept of residuals, and we saw residuals already in ANOVA, but here residuals for linear regression, it's based off of the same idea, but it also just feels entirely different. A residual for linear regression is the difference between an actual data point and our prediction, okay? So the residual is equal to the actual point minus the predicted point. And so symbolically, we write the actual point as y, and the predicted point is y hat. Okay? And the residual we call e as like error or something. So here our data points are 1, 2, 2, 6, 3, 4, and 4, 8. Okay. So let's, sorry. I'm jumping the gun here, okay? So that's the concept of residual, and we are going to decide that the best fit line is the line that minimizes not just the residuals, or actually I shouldn't say, it's not the line that minimizes the residuals, but the line that minimizes the squares of the residuals. Okay? For some reason we like to always square things in statistics. And so we try to minimize the squares of the residuals. So what we're going to do is we're going to take all the residuals and we square them and we add them up. Okay? And this we call sum of squares residuals. Right? And it feels entirely different from the sum of squares residuals that we saw for ANOVA. But believe it or not, the underlying concept is similar. It's the same thing. Okay, so that's the sum of squares residuals. Alright, so let's figure out the sum of squares residuals for these three candidate lines. Okay, let's start off with the worst line here. Okay, we know this one's going to be a bad line. Okay, so let's figure out the residuals for y equals 6. Okay, so you might want to put a table like this in your notes. We'll leave off. We just have 4 data points. So the residual is the difference between the actual point and what we predicted. Okay? So here, if my line is y equals 6, what would I predict my value to be when x equals 1? 6. Okay? So I would do 6, and the actual point is 2. So here I do the actual minus the predicted. So I do 2 minus 6, which gives me negative 4. Okay? And let's square that. So we get 16. Alright? Here, if my line is, if the actual point is 6, when x is 2, I predicted 6. So here, my residual is 0, and squared, I get 0. Over here, actual point is 4, and I'm predicting 6. So I get a difference of negative 2, and when I square that, I get 4. And here, my actual point is 8. I predict 6. I get 2, I square that, and I get 4. And so my sum of squares residual equals 6. Is that okay? Alright, so you might have space to keep going horizontally in your notebook. I don't, so I'm going to just do it over here. Okay. Let's do y equals 2. Okay, residuals for y equals, I'm sorry, y equals 2x. So if my data point is 1, right, the actual data point was 2, what would I predict y to be if, shoot, I've got to put hats on all of these, I apologize, because these are predictions. What would I predict my y to be if x is 1? 2, right? I just plug in x equals 1 and I get 2 here. And so there my residual is 0. And when I square it, I get 0. Okay. If y hat is equal to 2x, here my actual point was 6. What would I predict y to be when x is 2? I would predict it to be 4. And so my residual there is 2. And when I square that, I get 4. And here, my actual point is 4. If x were 3, I would predict this thing to be 6. I get a residual of -2. And when I square that, I get 4. And here I get 8 minus 8, 0, I get a residual of 0 squared is 0, and so my total sum of squares residual is 8. Alright, so compared to 24, a sum of squares that's equal to 24, this line, y equals 2x, this line is a better fitting line than this one. Okay, and let's go with this one then. Y hat equals 1 plus 1.6x. So when x is 1, okay, my actual data point was 2, and if I plug all of this in, 1 plus 1.6x, I would get 2.6 as my prediction when x equals 1. So here my residual is -0.6. So when I square that, I get 0.36. What is it over here? The actual data point is 6. When I plug in 2 here, I get 3.2 plus 1, 4.2. So here my difference is positive 1.8. I think this is, when I square that, I get 2.24, is that right? Something like that.
3.24?
Oh, 3.24, I'm sorry. Thank you. Okay, and I do the same thing for here. My actual data point is 4, but when I put in 3 for x, I get 4.8 plus 1, I get 5.8. So I get negative 1.8. I get 3.24 here. And lastly, I plug in 8 here, and I subtract off 4 times 1.6 gives me 6.4 plus 1, 7.4. I get a difference of 0.6. Square that, I get 0.36. And when I add all of these up, I get a sum of squares residuals equal to 7.2. So my sum of squares residual was 8. Here my sum of squares residual was 7.2. And here my sum of squares residual was 24. Alright, so of these three lines, this one is the best. Alright, well, that's nice and all, okay, but we certainly don't have the time, okay, those are three lines, and I knew which three lines, I mean, I knew three lines that might have been good, okay, but I mean, there's an infinite number of possible lines, and nobody has the time to go through an infinite number of lines and calculate all the sum of squares residuals for every single one to figure out which one is the best. So how do we figure out the best fit line? Okay, so I'm going to just kind of wave my hands and say magic, but not really. So some smart people use calculus to minimize a function. Okay, so if you can figure out the function for the sum of squares residuals, right? And then to minimize it, you basically take the derivative, set it to 0, find the critical points, and et cetera, et cetera, et cetera. And they found out that the equation that's going to minimize the sum of squares residuals always has a certain form. Okay, and this is what they found. Okay, the line that minimizes which is our best fit line, and because it minimizes sum of squares residuals, it's also often called the least squares line. Okay, so least squares line or best fit line, whatever you want to say, or also the linear regression line, because when you talk about linear regression, we are most it's become synonymous to least squares regression. So the line that minimizes sum of squares residuals will always pass through the point x bar, y bar. So it always goes through the middle of all of your data, or the mean. The mean of x and the mean of y. And that kind of makes intuitive sense, right? If it's going to be the best fitting line, it should predict, when I put in the average x, it should predict the average y. And the slope that it will have, okay, the slope is going to be r times the standard deviation of y divided by the standard deviation of x. And let me just talk about this slope for a little bit. Okay. So, what is slope? What is the slope of a line?
The rise over run.
Okay, we like to say the rise over run because that's what they teach you in algebra. But it's how much we predict y to change every time we increase x by 1. Okay? So if I change x by 1 unit, I predict y to change by this much. Or if I change x by this amount, I predict y to change by the numerator, right? Rise over run. So in this case, let's just cover up this r for a moment. If my slope were the standard deviation of y divided by the standard deviation of x, what would that mean? That means, let's say I start off in the center, x bar, y bar. Okay, this is the mean of x and the mean of y. If my slope were the standard deviation of x, so let's just say this were my slope, it's not, okay? That means if I go up one standard deviation in the x direction, I expect to go up one standard deviation in the y direction, all right? So if we're trying to predict the weight of a snake based on its length, we say a snake that is exactly one standard deviation above average in length will be exactly one standard deviation above average in weight. Now that seems reasonable, at least for snakes it seems reasonable, but it's a little bit of a too strong of an assumption or statement. Okay. Let's change the context here, and let's say we gathered a bunch of information, and this is actually how regression got its start. Let's say we gathered a bunch of information on adult males and their adult fathers. Okay, so let's say we got a bunch of 20-something-year-old males and their fathers, which are in their whatever, a little bit older. We'll say not so old that they're shrinking. Okay, and we measured their heights, and we found that in general, men who are taller than average, in general, had fathers that were taller than average. Okay. Now, if this were my slope, it would say, if I found a man who was one standard deviation taller than average, then I would predict the father to be one standard deviation taller than average. But that sounds like a very strong statement, okay? And if the son was 2 standard deviations above average, I would predict the father to also be 2 standard deviations above average. And that also seems a little bit too strong. So what we do is, what they found is that it's not the standard deviation y over the standard deviation of x. It's actually tempered by the correlation coefficient r. Okay? Because r always takes on a value between -1 and 1. So it never actually is going to get a value larger than s of y over s of x. It's tempered. So if r was 0.8, so pretty strong, it says, okay, well, if the son is 1 standard deviation above average, we would predict the father also to be above average, but not exactly a full standard deviation. We predict the father to be 0.8 standard deviations above average. Okay? Or if the son was 2 standard deviations above average, we would predict, okay, we predict the father to be quite a bit above average, but not 2 full standard deviations. We predict the father to be 1.6 standard deviations above average. And so the slope is r times the standard deviation y over the standard deviation of x. Okay, so that's what the slope is of the least squares line. Right. Is that okay? And so when we solve for the intercept, thank you. So if you think back to point slope form and you solve back for the intercept, we would get the intercept is equal to y bar minus the slope, which is b1 times x bar. I forgot to write the symbols here. Okay, so the regression line is of this format, and I apologize, I'm doing this out of order. So the regression line is in the form y hat is equal to b0 plus b1x, where b1 is the slope and b0 is the intercept, and y hat is our prediction for y. Okay? Yeah, it's a little bit different from mx plus b. We use b0 and b1, and we put them in this order. That's just what we do. So the intercept, which is b0, is that, and the slope is b1. Okay, and because I knew that, I picked these lines here. So for our data set,
Did you mean y bar?
where? Here?
Did you mean that to be the hat?
No, this is y bar. This is y bar minus v1 x bar. Okay? This one is y hat, our prediction for
I
one.
know,
So-
I was just, never mind.
No? Okay. I'm pretty sure it's all correct as Alright, so let's look at this, and we have x bar. So using our same 4 data points, x bar is 2.5, y bar is 5, and standard deviation of x and the standard deviation of y. I already forgot what these were. This was 2.582.
That is 1.291.
And yeah, and this one is 1.29. Great. Okay. So my slope v1 is equal to r times s of y over s of x. And I get I think we calculated r before to be 0.8. And s of y is 2.582. And this is 1.291. And so my slope v1 is 1.6. And then plug this in to get my intercept. Intercept v0 is equal to y bar minus v1 x bar. So my slope v0 is equal to 5 minus 1.6 times x bar, which was 2.5. And I get v0 equal to 1. So my overall line, the least squares line, is y hat equal to 1 plus 1.6 x.
Is that a 1? For the intercept?
Yeah, this is a 1. This is 5 minus 4, which equals 1. In Europe, they write their ones like this. Okay. Is that good? Alright, so what is the, let's just talk about the interpretation of the slope. Which in my case was 1.6, or in this example. So let me just get rid of this other line here. So this says for each additional, unit of x, we predict y to increase by the slope, or decrease if the slope is negative. Alright, so that's the generic form. And in our case, that means for each additional bedroom, we predict the number of closets to increase by 1.6. Right? Of course, you can't have 1.6 closets or anything like that, but overall, on average, we predict an increase to be 1.6.
Excuse me.
Yes?
So, I didn't get how did you come up with a y equals 1 plus 1.6x?
Oh, okay.
After.
So here I got my slope b0 to be 1
Uh-huh.
and b1 to be 1.6.
Oh.
Okay? And so I'm just taking the b0, so over here I got b0 equals 1, and I'm just putting that into my regression equation, and I'm just putting my b1, which is 1.6, right there. And so I get overall y hat equals 1 plus 1.6x.
Thank you.
Yes?
So, I get that you multiply r into it, but what if your r was like 0.2? And does that kind of make this slope irrelevant?
No, it just means you're tempering it quite a bit. So yeah, if r is 0.2, that means the relationship is really, really weak, right? Maybe there's a little bit of a relationship, but it's pretty weak, okay? So it's kind of like, I don't know. What's a weak relationship between two numeric variables? The amount of pizza someone eats in a week and the amount of potato chips they eat in a week, okay? There's probably some kind of relationship, right? People in general who eat more pizza than average probably, maybe, eat more potato chips than average, maybe. But it's a really weak relationship, if a relationship even exists, okay? And people who eat less pizza maybe eat less potato chips, maybe 0.2, okay? So we're just saying the relationship's pretty weak, r is equal to 0.2. So I say, oh, okay, well, now that I have this information, can I predict how many, so let's say the average person eats, I don't know, a quarter pound of potato chips, okay, in a week, I don't know. It's 4 ounces of potato chips, maybe more or less. So I say, oh, okay, well, I have a friend and he loves pizza. How many potato chips do you think he eats in a week? And you go, oh, well, if he eats a lot of pizza, maybe he eats a little bit more potato chips than average, okay? But you don't want to be like, oh, well, he eats 2 standard deviations above in pizza, he's going to eat 2 standard deviations above potato chips. You're just going to say, well, maybe he eats just a tiny bit more in potato chips. Because there's like such a weak relationship between the two, maybe, maybe you can say something, but probably not. Okay, so yeah, what's going on is your r of 0.2 indicates a pretty weak relationship. So yeah, anytime you make a slope, it shouldn't be saying a whole lot. Okay. So I don't know. I should come up with better examples than pizza and potato chip. I don't know. If your population were college students, that's, well, I don't know. They would probably eat quite a bit of junk food. At least for the guys. Our dorm rooms are terrible. Alright, so that is the interpretation of the slope. So here we would say each additional bedroom increases our prediction of closets by 1.6. Okay? And the key there is it changes our prediction. It doesn't actually change people's houses. It's not that when you add a bedroom to someone's house, the number of closets in that house increases by 1.6. Okay. And the intercept, what is our intercept? Our intercept happened to be 1, okay? And this is our prediction for y. When x equals 0. So this says if we entered a dwelling with 0 bedrooms, we predict the number of closets to be 1. So yeah, whenever you plug in 0 for x, the intercept is your prediction for 1. Sometimes it makes sense, sometimes it doesn't make sense. It wouldn't make sense, let's say we came up with a regression line for the weight of snakes based on the length of a snake. Okay? The interpretation of the intercept there would be our prediction for the weight of a snake if the length of a snake was 0. Okay? But you can't have a 0 length snake. That's a snake singularity or something, okay? It's not possible, and so the interpretation there doesn't make sense. Okay, so sometimes it makes no sense to plug in x equals 0, other times it does, okay? Yeah, you can have dwellings with 0 bedrooms, kinda, I don't know. A studio, does that count as a 0 bedroom? I don't know. It's called a studio, right? If it comes with a kitchen, and if it has no kitchen, it's called a bachelor. Which is really just a closet. So closet with a window. So that's an intercept. Okay. Let's see. Okay. So now let's. Oh, the other thing is there's a value called r squared. Okay. And this is called the coefficient of determination. It's a fancy name. To use the word coefficient for a lot of things. But it tells us how much of the variation in y can be explained by the regression. And for linear regression, so that's all we're doing in this class. For linear regression, when you square little r, you get big R squared. Okay. So that's that. Okay. So in our case, in this example, our little r is 0.8. So big R squared is 0.8 squared, which gives me 0.64. And this says, so the interpretation is 64% of the variation in y is explained by the regression, or some books will say, because our regression here is linear regression and only depends on x, you can also say 64% of the variation in y is explained by the variation in x. Okay? But these two things say exactly the same thing. And so what that means is that if we don't know anything about something or someone, or for this one particular variable, there's just variation, right? You go to different houses or different dwellings, some have more closets than others, and we just say, oh, well, there's variation in houses, or variation in dwellings, different places have different amounts of closets. Okay? That's the variation in Y. That's the variation in the number of closets. Okay? But then you say, okay, but rather than just saying all places are different and they all have different closets, okay, because that feels a little unsatisfying. Rather than just saying that's the reason why there's different numbers of closets, we say, you know what? Part of it is connected to the number of bedrooms in the house, and then we say, okay, well, if we take into account that different places have a different number of bedrooms, that explains about 64% of how different houses have different numbers of closets. Okay, so if we take into account the number of bedrooms, that explains 64% of the variation in the number of closets. But it doesn't explain all of it, right? Because you could have a 3-bedroom house with 5 closets. You can have a 3-bedroom house with 2 closets, or a 3-bedroom house with 8 closets, whatever. You can have different amount of closets for houses that have the same number of bedrooms. So part of it, there's still variation that's left over, okay? And that would be, 36% of the variation is still unexplained. But R squared tells us overall what percentage of the entire variation can be explained by regression. Alright, so now I have to give you some warnings about linear regression, or regression in general. Okay, because regression, it's pretty great. It's a great tool, okay, and Excel can do it, and a lot of different things can do it. But you have to be careful. Okay, so some warnings. All right, outliers can mess things up. So outliers can make you think there's a relationship when there's no relationship, can make you think there's no relationship when there is a relationship. It can just mess things up. So when you graph things and you notice some outliers, just be conscious of those things, okay? So for example, let's say we gathered a whole bunch of people, and we measured their IQ and their shoe size. All right? What kind of correlation do we expect to see? None, right? We would expect to see minimal correlation, if any, right? We don't expect someone's intelligence or IQ score to be related to their shoe size, okay? So, if we created a cloud of points, we would have people with little feet who are smart, people with little feet who have low IQs, and people with big feet who have high IQs, and people with big feet who have low IQs. And we'd see this scattering of points. Okay? All right. But then if we included Bozo the Clown. I don't know if you know Bozo the Clown, okay? He had just these unusually large feet, like freakishly large, okay? So he would be an outlier, and he was actually also very smart, okay? So he would be a point somewhere like this. And so if you did regression here, or correlation, it would try to accommodate this point, okay? It would try to minimize the square distance from there, and you would get this positive slope, okay? And you would incorrectly conclude that maybe there is a relationship between shoe size and IQ score, okay? So outliers can mess things up. Another is do not use regression to make predictions where you have not collected data. of people are not allowed, well, a lot of people are guilty of doing something like this, okay? So here's a silly example. Alright, let's say you have a child, okay, age 2, and you decide to measure the height of this child, okay, as time goes on. And so you go from age 2 through age 12, okay, and it seems every year the child gets taller, okay? And maybe from age 2 to age 12, maybe they doubled in height, okay? Well, if you used regression, and you say, oh, okay, well, here's the line. Let's predict how tall this child is going to be when he's 80 years old. You're going to predict he's like 60 feet tall or something, okay? And we know that that's not how it works, okay? That seems absolutely silly. Sure, it makes sense, okay? Linear regression might make sense in this area here where you collected data, but then to take that and extrapolate into the future or into the past to try to, or for any region where you haven't collected any data is extremely dangerous, okay? Because it only makes sense if there's a straight line relationship, and the height of somebody might be linear for childhood through, young adulthood, but it's not linear over the course of a life, okay? So you can't use linear regression, and we don't know what exists beyond a certain point. So, but people do this all the time, and government agencies kind of have to do this, but they also need to be aware that what they're doing is dangerous, right? Because they try to make policies for the future, okay? And sometimes they use linear regression, and the truth is nobody knows what the future is going to look like. Nobody knows what the future is going to look like. We can kind of make our predictions and guesses, and there's some smart people working on it, but the truth is nobody knows what the future looks like. All right, and the last one is correlation is not causation. Just because there seems to be a relationship between two numeric variables, or even for all of the other statistics that we've done, where we see a relationship between two variables, it does not mean there is a cause and effect relationship. And this is it's also very tempting to come to cause and effect conclusions. Say, oh, every time we saw this, the amount of this hormone, and in people with higher amounts of this hormone, it seems like they were healthier, so we should start injecting this hormone into people. That's not gonna may or may not actually work, okay? So you can't assume that one causes the other. It could be that better health causes higher hormone production or whatever. We don't know, okay? So this is also something dangerous. Okay. Anyway, do your homework, and then we'll see you guys next week for just kind of a recap and summary of everything that we've done. So, see you guys.